Hi friends, welcome to our channel. From the previous videos we have studied few physical quantities that is used to describe a motion. Now in this video we shall see how those physical quantities are related to each other. First of all, consider an object that is moving along a straight line. Let u be the initial velocity of the object, and the object is moving with a uniform acceleration a. Now if the final velocity of the object is v and the distance covered by the object in time t is s, then we shall relate all these quantities with a set of equations. That is, v is equal to u plus at, s is equal to ut plus half at square, 2as is equal to v square minus u square. These equations are called as equations of motion. That is, we are showing the dependency or how the physical quantities are related to each other using equations of motion. Now next we shall study how to derive these equations using graphical method. Now let's start with the first equation, v is equal to u plus at. This equation is also called as velocity time relation. Alright, now for this we need a velocity time graph of an object that is moving with uniform acceleration let's say a. Okay, so you can see there is a graph here, there is a velocity time graph here, and for this object that is having a uniform acceleration, we can see that from this graph the initial velocity of the object is at point A. So let's mark here as u, and then from point A the velocity of the object increases to point B, right? So this point B represents the final velocity of the object. Let's denote it by v. So this increase in velocity from A to B, that is from u to v, is at a uniform rate a. That is what we mentioned initially. This is the velocity time graph of a object that is having uniform acceleration. Now we have drawn perpendiculars from point B onto the time axis and velocity axis. So from this graph we can see that the initial velocity u is represented by OA. So initial velocity is represented by OA, and final velocity v is represented by this line, right? BC. This is the final velocity BC. So this line represents the final velocity, and the time interval taken is time interval is represented by OC, T. So we can mark T here, right? Now, as we said earlier, the velocity is increasing from U to V. So this change in velocity or this increase in velocity is represented by BD, because the velocity is changing from this point to this point. So this is the increase in velocity. So change in velocity is represented by BD. I hope it is clear. Now, from the graph, we can say that BC, this line BC is equal to BD plus CD. This is C. Okay. BC is equal to BD plus CD. It's normal logic, right? Now, let's substitute BC and CD. Okay. What is BC? BC is final velocity, right? So let me write that expression once more. BC is equal to BD plus CD. Now, before substituting BD plus, can I write CD as OA? CD is equal to OA, right? CD is equal to OA from the graph. Okay. Now let's substitute the values. BC is final velocity. Okay. Let's write BD. And what is OA? OA is initial velocity, U. So BD becomes V minus U. Alright. So let's mark this equation as equation number 1. That is BD is equal to V minus U. Now next we know that acceleration is equal to change in velocity by time, right? That's what we studied previously. Acceleration is change in velocity by time. Now what is change in velocity from our graph? Here we have written change in velocity is equal to BD, right? And time is OC. So BD by OC. And we know OC is time, right? So I have substituted T for OC. So what do we have now? Acceleration A is equal to BD by T, or I can say BD is equal to AT. Let this be my second equation. Now we have a first equation here and we have our second equation here. What do you understand from this equation, or what you can say? BD is equal to V minus U and BD is equal to AT. Here right hand sides are equal. That means left hand sides will also be equal. So from equation 1 and 2, I can say BD is equal to V minus U is equal to AT, right? That is V minus U is equal to AT, or V is equal to U plus AT. This is our final equation. Now next, let's derive the second equation. S is equal to UT plus half AT square. This relation is also called as position-time relation because it gives a relation between distance and time. So for this derivation also, we require the velocity time graph, just like the previous one. Now here we are finding the distance the object has travelled in time t under the uniform acceleration a. We are finding the distance covered by the object s in time t under uniform acceleration a. Okay. So now from a velocity time graph, we know that the distance covered is area under the graph. So for this velocity time graph or for this object, the distance travelled will be area under the curve, right? So that's the area, that is this area, or we can say area OABC. So here OABC is a trapezium. So this area will give the distance travelled by the object during the time interval t and under uniform acceleration a. Now I can draw a perpendicular like this and name this t. So now this trapezium becomes a rectangle AOCD and a triangle ADB. So here my trapezium will be, this is area of a trapezium, right? So now I can split this trapezium as a rectangle ADCO and triangle ABD. Right? So now let's find the area of the rectangle and area of the triangle. What is the area of the rectangle? It is, so S, distance travelled S is equal to area of the rectangle will be OA into OC. OA into OC, that is length into breadth, plus area of the triangle is half into area of triangle is half into base into height. This is the formula for area of a triangle. Here base is AD and height is BD. So this is the area of a triangle. Once again, what have we done here? We are finding the distance covered by the object in the time interval t, which is moving under a uniform acceleration a. And we have a velocity time graph. So we are finding the distance from the velocity time graph, and we know that the distance traveled by the object from a velocity time graph is given by the area under the graph. So this is the time interval that we are considering. OC is the time interval that we are considering, right? So for this time interval, the area under the graph is the shaded portion, this shaded portion. Now this shaded portion comes to be a trapezium. So the distance travelled by the object is the area of the trapezium OABC. Now for the calculations to be easier, what we are doing, we are splitting this this trapezium to a rectangle and a triangle by drawing a perpendicular AD. So the distance will be equal to the area of the rectangle ADCO and the area of the triangle ABD. Now, simple geometry, area of the rectangle is OA into OC plus area of the triangle will be half into base AD into height BD. Okay. So now let's continue. We know OA is the initial velocity, right? From the previous derivation we know OA is the initial velocity and OC is the time interval. So let's substitute that, U into T plus open bracket half into AD. What is AD? Isn't it AC same as AD same as OC? AD, since AD is parallel to OC, AD will be same as OC from the graph into OC into BD. Okay. So this is UT plus half into OC is what? OC is T. And what is BD? From the previous derivation we had BD is equal to A into T, right? Once again, B acceleration was change in velocity by time, right? So change in velocity is BD for us in the from the graph by time T. So from here BD is equal to A into T. This we have done in the previous derivation. So we will substitute AT instead of BD. I hope you guys got how we got this. BD is equal to AT. Acceleration is equal to change in velocity by time. From the graph we have change in velocity as BD. This is the change in velocity BD. So BD is equal to A into T. So let's substitute AT instead of BD. So now what do we have? S is equal to UT plus half AT square. This is the final equation that we need. That is position time relation. Next, let's derive the final equation, that is 2AS is equal to V square minus U square. This relation or this equation gives the relationship between position and velocity. So this equation, like the previous one, is derived from the velocity time graph, and we'll use the area under the graph to get the distance covered by the object. But we'll use a different formula to get the area under the graph. That is, now from this velocity time graph we know S is equal to, or the distance travelled by the object during the time interval T is S is equal to area of trapezium OABC, right? This is what we have seen even in the previous derivation. OABC. The area of the trapezium OABC will give the distance covered by the object during the time interval T. Now here we'll use the formula for area of a trapezium instead of splitting the graph into a rectangle and a triangle. So basically, the derivation is like the previous one, but we are eliminating the term time. We don't want time in our equation. So area of a trapezium is, let me tell you what is area of a trapezium first. Area of trapezium is equal to, this is a trapezium, right? This is how a trapezium will look like. It will have two parallel sides and non-parallel sides. Now, to find the area, you need to add the parallel sides and then multiply that sum with the height. This is the height. Multiply with this height, then divided by 2. This is area of a trapezium. That is, add the parallel sides, multiply it with the height, and then divide the complete answer with 2. So let's use this formula to find area of this trapezium OABC. Here, what will be our parallel sides? It will be OA and BC, right? So OA plus BC. This is our parallel sides into. The height is OC. This is the perpendicular height, OC, divided by 2. Alright. Now, from our previous knowledge or from our previous derivation, we know OA is u, that is the initial velocity, plus what is BC? BC is the final velocity, and OC is t, divided by 2, right? So this be the first equation. Now let's continue here. What was our first relation? The velocity time relation. V is equal to u plus at, right? From this relation, like we are rearranging this relation, V minus u is equal to at, right? From here, can I write t is equal to v minus u by a? I just brought down acceleration into denominator. So let this be my second equation. I will multiply my first and second equation. Multiply first and second equations together. So that is, I'll multiply right hand sides together. That is s into t is equal to, and then I'll multiply my left hand sides together. U plus v by 2 into t multiplied by this, right? V minus u by a. I hope this is not confusing. I multiplied these two sides, that is s into t, and then I multiplied these two sides, u plus v by 2 into t, and multiplied by v minus u by a, right? So as I mentioned earlier, we are trying to eliminate t. So we'll cancel t from here, and then s is equal to u plus v and v minus u by 2a. Now, here we are going to use an identity that is familiar for you. You all remember this identity, a square minus b square is equal to a plus b into A minus B, right? So we are going to use this identity here. Doesn't this side look like this? This is A plus B into A minus B, U plus V into V minus U, right? So this I can write as V square minus U square by 2A. Now rearranging this equation, I get 2AS is equal to V square minus U square. This will be my final relation. I hope the identity part is not confusing. A plus B into A minus B is equal to A square minus B square. Here, in case if this is confusing, like here it is U plus V and here it is V minus U, I can write this as V plus U. It's the same, right? Now V plus U into V minus U is equal to V square minus U square. So I used this identity and rewrote V plus U into V minus U as V square minus U square by 2A. Now taking 2A to this side, 2AS is equal to V square minus U square.